I'm Shinji Tsuneyuki. I'm from the Department of Physics, the University of Tokyo. First of all, I'd like to thank the organizers for kind invitation to this conference. Today, I'd like to talk about crystal structure prediction by data assimilation of incomplete X-ray powder diffraction data. The word data assimilation is often used in the context of weather forecast. In the simulation of weather forecast, they solve an equation of fluid dynamics. However, unfortunately, they don't know the complete initial condition to start the simulation. So they use data observed at a finite number of observatories and interpolate the data and start the simulation. As time passes, the simulation comes to deviate from the reality. But fortunately, they can get the next data from the same observatories, and they can refine the initial condition to meet the data. The method is called data assimilation. What I'd like to do here is to use the idea of this data assimilation for crystal structure simulation. In this view graph, I'd like to summarize the purposes of this study. A prerequisite in the study is that we use the density functional theory or accurate interatomic potential model to calculate the potential energy of the system. The relative stability of different metastable structures might be somewhat wrong, but we rely on local stability and the structure. A problem here is that prediction of crystal or molecular structures becomes difficult as the number of atoms increases, since the number of possible atomic configuration diverges. So the purposes in the study are twofold. First, we would like to accelerate crystal structure search by assimilating experimental data, or more specifically, incomplete X-ray powder diffraction data. Second, we would like to predict positions of hydrogen atoms in materials because it is hard to determine the position of hydrogen atoms only by experiments. At the beginning, I'd like to show you a typical example where we'd like to use the data assimilation method. This is the X-ray powder diffraction data for the hydrogen sulfide, a high TC superconductor at high pressure. The material and its superconductivity was found in Max Planck Institute by Eramet's group, but the data shown here is the one taken at Spring 8 in Japan. This experiment is done at about 150 GPa using the diamond anvil cell. So the diffraction angle observed here is quite limited, from 10 to 25 degrees. In this range, only 4 or 5 peaks are attributed to the hydrogen sulfide. Therefore, we cannot determine the crystal structure of this material by the Rietveld analysis. In such a case, we often perform first principles simulation of the structure. One of the simplest methods is the simulated annealing. Starting from the random distribution of atoms, we do molecular dynamics simulation at high temperature and gradually decreases the temperature. Finally, if we are lucky, we can get the ground minimum of the potential energy of the system. As you know, however, the success rate is extremely small in general, and we usually get amorphous structures. This is because possible structures are so many that we cannot reach the correct answer in a finite time. I will show you later that the experimental information helps and drastically accelerate the simulation by the data assimilation, even if the information is limited and incomplete. The data assimilation we are proposing for crystal structure prediction is based on Bayes' theorem for the conditional probability. Here, rho of Rix is the conditional probability of atomic structure represented by R when diffraction data represented by Ix are known. By the Bayes' theorem, it is proportional to the product of rho of R and the conditional probability rho of Ixr. At finite temperature, rho of R is written by the inverse temperature beta and the potential energy E of R. On the other hand, the conditional probability rho of Ixr can be written by a so-called penalty function d. D is an arbitrary function which becomes large as the calculated diffraction intensity Icalc deviates from experimentally obtained one, Ix. As a result, the conditional probability rho of Rix, which we would like to know now, is written with a new cost function f of R and Ix, defined by a sum of the potential energy E of R and the penalty function d. In the data simulation, this cost function f is used for the simulated annealing. We have various choices for the penalty function d. But as a first trial, here we define d by the crystallinity lambda. Here n is the number of atoms in a simulation cell, and alpha is a control parameter. In the definition of lambda, the denominator is the integral of the calculated diffraction intensity in the range of the measurement in the real experiment. On the other hand, in the numerator, the sum are taken at the angles where diffraction peaks are observed in the real measurement. Therefore, in this definition, we utilize the diffraction angles obtained by experiments, but do not use the diffraction intensity itself. The merit of using this crystallinity is that the method is robust against preferred orientation effect, which is often problematic for crystals with large anisotropy. To make it easier to understand the data simulation, I will show you a simple example. This is a simulation of silicon. First, we put 64 silicon atoms randomly in a cell and calculate the powder diffraction data as shown in the right panel. We know from experiments that crystalline silicon should have 3 diffraction peaks in this angle range. From this information, we can set up the crystallinity lambda and the cost function f and start simulated annealing. You can see that the 3 diffraction peaks grow up soon and the crystal is formed. We test the method with a more complicated crystal structure of SiO2 silica. Silica have several polymorphs, but I chose three well-known polymorphs: low cristobalite, low quartz, and calcite. Calcite has 16 SiO2 units in a unit cell, and the structure is quite complicated, as known from the very low symmetry. The diffraction intensities calculated using non-crystal structure are shown in the right. For the data simulation, we use the information of diffraction peaks from 20 to 45 degrees enclosed in a red frame. The cost function here is made by the crystallinity for these peaks. These are the results for each polymorphs, and I will show you the movies of successful simulation. The number of atoms in the simulation cell is 96, 72, and 96, respectively. The unit cells are shown by white frames. The success rate is 109 in 500 trials for cristobalite, 148 in 500 trials for low quartz, and 12 in 500 trials for calcite. The success rate for calcite is not so large, perhaps because calcite has a very low crystal symmetry. But if you know the complicated structure of calcite, it's quite a good number. This figure shows how the potential energy E and the cost function F changed in the successful simulation. The abscissa is the crystallinity lambda. The simulation started from the left, while the crystallinity, where the crystallinity is less than 0.7. And the simulation ended in the right end, where the crystallinity is 1. The potential energy E shows a large potential barrier between the start and the end, while the cost function F has no barrier, and so the system smoothly went down to the end. This is how the data simulation works. Now, let us use the data simulation for the hydrogen sulfide at high pressure. The left movie is a typical result of ordinary simulated annealing, and the right one is the successful case by the data simulation with the same speed of simulated annealing. Within our trial, we have never succeeded in crystallization by the ordinary simulated annealing, while the success rate of data simulation is 13/20 and quite high. Let us go back to the problem of choosing the penalty function d. So far, we have used crystallinity, which utilized the information of diffraction angles. Another simple choice is the usage of correlation function coefficient between experimental and theoretical diffraction intensities. As I have already mentioned, the choice 1 is robust against preferred orientation effect, but it is difficult to use it when the small peaks are buried in the large noise. However, in general, the success rate is larger if we use the second choice, where we utilize more experimental information. Furthermore, In the second choice, we treat the signals and noise on the same footing, and so we don't have to select the peak positions before the simulation. This is an example of the data simulation with the second penalty function based on the intensity correlation coefficient. The target crystal is SiO2 coside, and the simulation cell contains 48 atoms. The black line is the ideal diffraction data with a slight broadening. With this data, the success rate is 60%. The red one is the data with large artificial noise. Even if the data is so noisy, the success rate is 5%, and it is comparable or larger than the success rate with the crystallinity. This is another example of data simulation. Y2C is a layered material and absorbs hydrogen up to nearly 3 for Y2C chemical unit. When the number of hydrogen is less than 2.6, it is concluded from neutron diffraction that hydrogen atoms are located either at octahedral sites or at tetrahedral sites between layers. Recently, more hydrogen-rich materials have been synthesized, but their structure is still unclear. So we simulated its structure with data simulation. What we found here is that when the number of hydrogen increases, some of the hydrogen atoms prefers forming CH bond with the carbon atoms surrounded by yttrium atoms rather than fully filling the interlayer octahedral and the tetrahedral side. Finally, I'd like to briefly mention another approach for data simulation, which we call combined optimization method. In this method, we treat the potential energy E and the penalty function D independently of each other by using the gradients to avoid local stable solutions. An advantage of this method is that we can easily utilize multiple experimental data. This is a summary of my talk. We are proposing data simulation for crystal structure prediction or determination. X-ray diffraction data help crystal structure simulation even when the data are incomplete and Rietveld analysis does not work. Here we mainly adopted simulated annealing, but simulated annealing is not the only way for the minimization of the cost function f. There might be even better ways to do the structure simulation with data simulation. Finally, these are my collaborators, and the present work is supported by several grants from MEXT in Japan. Thank you very much for your kind attention.